This video is about rates, or how fast a reaction proceeds. You should already be able to explain collision theory, describe the rate of reaction, and describe the factors that affect the rate. We will review that. And by the end of the video, you should also be able to write a rate expression in order to calculate concentrations, times, and rates for various data. The question of the video is, catalytic converters in cars decrease air pollution by converting NO, which leads to acid rain, and poisonous carbon monoxide to N2 and CO2, according to this red reaction. So we want to know, how is the rate of consumption of carbon monoxide and nitrogen monoxide related to the rate of production of nitrogen and CO2? So how fast do reactions proceed? Collision theory states that when two chemicals react, they have to actually collide with the proper energy and orientation. So in the picture that we've seen before and last year, if they collide where bromines actually collide, the bromines may now react and form diatomic bromine, where N and O will separate. And again, in B, the bromines reacted and formed bromine diatomic. But in the last equation, C part, the O's are what collided and it just bounced off. So there was no reaction. So we're saying that they have to collide in the proper way. What affects this rate of reaction? Well, we have to get a lot of collisions, so that some of those collisions will never work, right? So the more collisions we have, the better chances that it will work. So we can increase it by increasing the temperature of the system to make them move more, increasing the concentration of the reactants so that there are literally more reactants to have collisions, increasing the pressure of gaseous reactants so that we're closer together so they'll have more collisions, increasing the surface area of a solid, so instead of just colliding with the outside, they could collide with whatever used to be inside, introducing a catalyst, and we'll talk about that in more detail later, but it provides an alternate pathway, or agitating and stirring the solution to increase collisions. The rate will decrease if you decrease any of these factors, such as temperature, molarity, pressure, or surface area, or if you introduce an inhibitor, something opposite than a catalyst that will slow it down. The reaction rate has nothing to do with how much of the reactants actually react. This is depending on the limiting reactants and the equilibrium. So we're not saying we're not looking at the exact equation and looking at the moles in that equation. So the rate of reaction can be determined by monitoring the change in concentration of either the reactants or the products as a function of time. So in the first reaction as we go, the red is supposed to represent the color that you see in the bottom beaker, and as you go it's changing into something else. So at first you had all A's and no B's. B's might be colorless, but we wouldn't be able to see them in the molecule diagram. And as it starts to react, some of the reds are turning to blues, and eventually a lot more of the reds are gone and the blues appear. And so we can monitor it, like they're saying, every 20 seconds. You can either be monitoring how quickly the red goes away or how quickly the blue appears, which would be the colorless color, right? So we're monitoring either the reactants, which were A, or the products that were B. And so the reaction rate is a change in the concentration of that reactant or product with time, so the molarity per second. And this can be calculated using a rate expression in terms of the reactants or the products. So if A was a reactant and B are the products, you can either look at the rate as the change in A over change in time, or in change in B over change in time, right? Now notice that the rate of A is negative and the rate of B is positive. That's because A is decreasing over time. So we like to show that as a negative value, whereas B is increasing over time, so we show that as a positive value. And that's really important. You should write that on your notes. So if we were to graph this change over time, which is basically just a slope of a line, right? The A should decrease over time, and that's why our graph is showing that decrease in the black. And then the B would increase over time, which you see as the increase over here on red. Here's an actual equation. Instead of just A's and B's, we have chlorobutane in a reaction versus time. So originally you had a 0.1 molar solution, and the student monitored how much concentration it had over time every 50 seconds, and then it turned into 100 seconds because it was going too slow for them. And then eventually, skipping through. And they monitor how much of that chlorobutane was there, maybe using the spectrophotometer we saw in our activity. And what they can do then is find the average rate of reaction over time, each interval, by doing a change in concentration over the change in time. So if you're looking at the first set of data, we would say the concentration changed by 0.1 minus 0.095, and then divided by the change in that time. So 0, 50 minus 0. And that's how they got the 1.9 times 10 to the minus 4th. That's the rate. But notice the rate changes every time we go to do it. So they did it for each one. They did the concentration change divided by the time change, you got 1.7. Or this concentration change, 0.07 minus 0.05 divided by 150 minus 100. You got this number. So that it's decreasing as the reaction proceeds. Why would that be? I want you to think about why would it go slower as the reaction keeps going. The answer is because as the reaction goes forward, there's fewer collisions. There's less stuff to collide because we've reacted it all. So if there's less concentration, there's going to be less collisions, and if there's less collisions, the reaction rate is going to go slower, right? It's going to take longer for those 2 or 3 last particles to find each other and collide the right way. So looking at this graph again, anything that's decreasing over time has a negative slope. And in order to, when you plot it, it's not a straight line, right? Because at first it's going to react really fast, and as you go, it's going to react slower and slower and slower. So you have that red curve like this. The slope of a line tangent to the curve at any point is that instantaneous rate. How fast is it going right here on this one part, right? And so if you wanted to find it, you would do the change in concentration versus change in time in that one spot. But that instantaneous rate is not the same rate as right here because that slope is much less steep, right? Because it's going slower. So you're finding all these individual rates at specific times as you go. And so here's a reaction what was going through. That chlorobutane reacting with water is forming a hydroxide group and an acid. The reaction is a 1-to-1 ratio. So every time you lose the chlorobutane, you're forming this other particle at the same rate. So the only difference is this was negative because it was being used, and this was positive because it was being formed. But what happens if another reaction does not have a 1-to-1 ratio? How can you figure out how much another particle is forming? So an example of HI forming at the rate of half of which hydrogen disappears, notice that when they say that, that means whatever the hydrogen was, it was disappearing, so it was negative. The HI must be forming, so it's positive, at half the rate. So that's why it has an equation, coefficient of 1/2. So that's how we would read, and this is how we would write the equation. So the reason why we do that is actually because it's just the inverse of the coefficient. So for any substance, the reactants are always going to have a negative value because they're decreasing. The reactance coefficient A would be inversed. So if it has a 2 in front of it, it's going to be half the rate. If it has a 3 in front of it, it's going to be a third of the rate. And any of the products are going to be positive because they're forming, and the same thing with their coefficient. So if their coefficient was 3, it's going to be forming at the 1/3 rate, or if it was coefficient of 4, it would be forming at the 1/4 rate. So if we were to write rate expressions, which we can use to calculate the concentrations at any given time, we would just write them as, since hydrogen is a reactant, negative. The coefficient was 2, so negative 1/2, change in hydrogen over change in time. I can also monitor oxygen over time, so it would be just negative. There's no coefficient because 1/1 is 1, so we're going to keep it 1. Change in oxygen over change in time. And if we wanted to talk about it in terms of how much water is formed, which would probably be the easiest because you see drips of water, right, forming, it would be the positive value because it's a product, 1/2 because that was a coefficient, of change in water over change in time. What we're showing that is every time you lose a hydrogen, you gain a water because they have the same rate, but oxygen happens at a little different speed because it has a different coefficient, right? So every time you use 2 hydrogens, you're only losing 1 oxygen, so that's why they have a different ratio. Let's do it again for oxygen converting to ozone. So then the oxygen would have a negative rate because it's being used at a 1/3 value, and then the ozone is being formed as a product at the positive value of 1/2. This is the formulas we can use to then calculate questions. So you're kind of writing your own formula for the reaction in order to calculate number 2. This is the real question that will come up. How is the rate of disappearance of oxygen related to the rate of appearance of ozone if the ozone that they detected was happening at 6 times 10 to the 5th meters per molar per second? So you can use the equation that's written that we just did, right? So this is the way the AP thinks you're going to do it. So we're going to put, this is the equation we just wrote. You need to use it in the next part. And we're going to put 6 times 10 to the 5th molar per second in as the rate or change in ozone over change in time. We're going to keep the coefficients there because that's how we can convert from one element into another or one compound into another. And then we're going to solve for x. So we're going to take half of 6, which is 3 times 10 to the 5th, and then to divide by the negative 1/3. In order to get 9 times 10 to the 5th. If you don't believe me, put in your calculator. What we're saying is that the oxygen will be used, and I'm sorry, I missed the negative, it should probably be negative, used at 9 times 10 to the 5th molar per second every time we make the ozone at that rate. Another way you could do it, if you don't like these fancy do things, you need to know how to do this in case they're on the multiple choice part, so they might ask you which one's correct or which one's incorrect. You could also just use dimensional analysis, and this is the way I choose to do it. So I take the number in the question, place it over 1, multiply by a new fraction. Whatever the initial substance was goes on the bottom so that they are catty-cornered from each other. The ozone had a coefficient of 2, so it has a coefficient of 2 here as well. The oxygen had a coefficient of 3, so it does here as well. And then I just multiply and divide, just like regular dimensional analysis. And hey, guess what? Same answer. So if the question requires you to write a rate expression, then I write one. But if it doesn't require it and it just says, hey, what's the rate? I don't use those because I think they're confusing, and I just use regular dimensional analysis. Here's another type of question that can come up in this topic. The student obtained the following data for the change in concentration of bromine. Calculate the rate from 0 to 50 seconds. So remember again, the rate is going to be found by change in concentration or change in time. So we're going to do final minus initial, 0.0101 minus 0.012, and then you divide by the change in time. So we're just doing change over change. And so that was negative 3.8 times 10 to the minus fifth. And that was only for that one part, right, that change. Then it says calculate the average rate from 50 to 100. So we'll do the 50 to 100 data. So these two concentrations, the second two, minus the 50 and the 100 times. So notice that it's just the same work, right? 0.01 minus 0.0846 divided by 50. And then it says, explain why the rate is not the same for each and how it was obtained. So we always find the rate by doing concentration change divided by time change. And the reason why it's not the same is because bromine must have been being used as we go, right? Because you see how the concentration is dipping. And so the reason why the rate's not the same each time is because it's being used up. So then therefore, the values, the amount of particles you have to collide will be decreased. And so you'll have a harder time having those actually react. Now you might also say, why are these values that we just calculated not the values that are up here? Remember, these values were found by doing a tangent to the line. Exactly at that time, what was the rate? So instead of over 50 seconds, maybe it was at that 1 second. And so they're a little off from the values here because these are instantaneous at that moment, and these are over the span of a time, right? So back to the question in the video to wrap it up. Catalytic converters were using their chemistry in order to convert CO and NO, which are poisonous and bad gases, to N2 and CO2, which are a little bit better at least. And we want to know how their rates were related. Well, the rates are related by doing these expressions. So CO and NO were both being lost over time, negative, and they both had a coefficient of 2. So 1/2's in the front. The N2 and the CO2 are both being formed, so they're positive. N2 had no coefficient, so we'll leave it alone. And the CO2 had a coefficient of 2, so it's 1/2. What we're basically saying is every time a CO and an NO are used, a CO2 is formed. They're all at the same rate. Nitrogen's forming at double that, being formed at half of that rate. So every time CO2 is being formed, only one N2 is being formed. At this point, you should be able to construct rate expressions and try to use them in calculation.